Alright, so in this video, I'm going to solve the equation 1 to the power of x is equal to 2. So, before we even start solving this, if, let's say x is equal to 1, then I have 1 to the power of 1, which is equal to 1. And if x is equal to 2, then I have 1 to the power of 2, which is also equal to 1. And you can go even 1 to the power of 10 is still equal to 1. So you may be thinking, what possible value of x can make 1 to the power of x equal to 2? So let's try solving this. What I'm first going to do is start by taking ln of both sides. So I get ln of 1 to the power of x is equal to ln of 2. And ln is the same thing as the natural log. And the reason I took the ln on both sides is because it comes with a property that states that if I have something in the form ln a to the power of b, I can move this exponent b to the front, so this turns into b times ln a. So in this case, I have ln 1 to the power of x, and I can move x to the front. So I get x times ln 1 is equal to ln 2. And you may be thinking, we could just divide both sides by ln 1 and x would equal ln 2 over ln 1. However, the only problem with this is that ln 1 is equal to 0. And remember, anything divided by 0 is undefined, so this would be undefined. So we know that this equation has no real solution, but it could still have imaginary solutions. So to actually solve this, I'm going to use something known as Euler's formula. And basically what this formula is if I have something in the form e to the power of I times theta, this is equal to cosine of theta plus I times sine of theta. And I know to many of you watching this video, this may just sound like a bunch of gibberish, but just hang on. So let's say that theta is equal to 0, right? Say that theta equals 0. So now I get e to the power of I times 0 is equal to cosine of 0 plus I times sine of 0. Cosine of 0 is 1 and sine of 0 is 0. So I get this all is equal to 1. Now, what if we say theta is equal to 2k pi? And k is just a substitution for all real numbers. So now I get e to the power of I times 2k pi is equal to 1. Because all we did was we just substituted theta in for 2k pi into this same thing. So now, because this is equal to 1, we can remember our first equation, which we started with 1 to the power of x equals 2, we can substitute in this for 1, meaning I get e to the power of I times 2k pi to the power of x is equal to 2. So just think of this as 1. So I have basically 1 to the power of x equals 2. And now, with this, I'm going to take the ln, or natural log, on both sides. So I have ln e to the power of I times 2k pi to the power of x is equal to 2. So I'm going to now bring this x down using property of natural logarithms. So I get x times ln e to the power of I times 2k pi is equal to 2. is equal to ln of 2, because if you take ln on one side, you have to do the other side. And now I can also move I times 2k pi to the front. So I have I times 2k pi times x times ln e is equal to ln 2. ln e is simply equal to 1. So I get x is equal to ln 2 over I times 2k pi. And now I'm going to multiply this by I over I. So I get x is equal to negative I times ln 2 over 2k pi, because I squared is negative 1. So this is my solution. Alright, so in this video, I'm going to be solving the problem 9 to the power of 900 minus 9 to the power of 901. So, to solve this, I'm going to first start by evaluating my terms. So we have 9 to the power of 900 and 9 to the power of 901. And these two terms are pretty similar, except that the exponent for 9 to the power of 900 is 1 less than the exponent for 9 to the power of 901. So the easiest way to solve this is to simplify this as much as we can. And a way to do that is to factor out a term. Well, 9 to the power of 900 is actually a factor of 9 to the power of 901. So all we have to do is rewrite 9 to the power of 901 as something times 9 to the power of 900. Well, we can use properties of exponents to do this. So I'm actually going to rewrite 9 to the power of 901 as 9 to the power of 900 plus 1. And now I can use the exponential property a to the power of m plus n is equal to a to the power of m times a to the power of n. So I get 9 to the power of 900 minus 9 to the power of 900 times 9 to the power of 1. So now from here, these two terms have the number 9 to the power of 900 in them. So I'm going to factor out 9 to the power of 900, which is what I said I was going to do at the beginning of the video. So now I get 9 to the power of 900 times 1 minus 9 to the power of 1. And this is equal to 9 to the power of 900 times 1 minus 9, because 9 to the power of 1 is the same thing as 9. Now 1 minus 9 is equal to negative 8, so I get 9 to the power of 900 times negative 8. Now from here, I said I was going to simplify this as much as possible. And we can't really get the exact value because 9 to the power of 900 is such a big number that we can't actually get the exact value for that. However, what we can get is the simplified value, and we're going to simplify it as much as possible. So I'm actually going to move this negative sign to the front. So I get negative 9 to the power of 900 times 8. And this gets me negative 3 squared to the power of 900 times 2 to the power of 3. We're simplifying these terms as much as possible. So I'm going to use a quick exponential property that states that a to the power of m to the power of n is equal to a to the power of m times n on 3 to the power of 2 to the power of 900. So I get negative 3 to the power of 1800 times 2 to the power of 3. So this is my final solution to this equation. Now, if you haven't already, please make sure to subscribe, leave a like, and even show this to any of your friends and family. That would support me a lot. I have a bunch of other videos similar to these on my channel, and if you're up for any challenges, I have a bunch of those, so please make sure to check them out. And thank you for watching. Bye.